Do not worry. Um, yeah, do not worry because you guys can go look at the recording from last class if you're ever confused about how we got those equations. But right now we're gonna be practicing how to use those equations in the problems. And then I know some of you guys did your homework, but for the people who didn't, that's totally okay. It's fine if you didn't. I like that's for you guys to practice. So if you guys feel confident, you guys didn't need to. But yeah, let's go through some problems. Let's just do this. Yeah. Share. Tell me when you guys can see my screen. Okay, welcome to Intro to Physics. This is the third class of this session. So I hope you guys are liking it. Third week. We're gonna be going into first, actually, we're gonna be reviewing some kinematics problems. So if you guys weren't here for last class, feel free to check out the recording if you guys are ever feel confused because we do go pretty in depth in that class and we answer a lot of the questions some of the kids have, which you also might have, but um you're gonna have to trust the equations that we're gonna be using right now though, if you guys weren't there for last class. So I'll give you guys uh t- two 2 minutes to solve this problem and see where you guys get. Please private chat it to me or Ethan um once you get the answer. But yeah, until 2:14. Does anyone else need a little more time or are you guys good? I got three answers. I don't know about um Ethan. Ethan, how many answers did you get?
I got one.
Okay. I'll give you guys another 30 seconds. Okay, yeah, take your time. Don't worry. Okay. Um, so I'll just go over the answer now since I think everyone's had a bit of time. But it's okay if you haven't solved it yet. I'll just be walking through it with you guys. So um we know that the cyclist starts at the initial, the subscript. If you guys weren't here for last class, this just means the initial velocity, the subscript. Let me hide my name real quick so it doesn't. Okay. Um, the subscript just means the initial velocity equals 8 meters per second, correct? And the acceleration, again, this is constant acceleration, equals 2 meters per second squared, correct? And our last variable we have is velocity, the final velocity, right? Equals 20 meters per second, correct? Um, so we have our three variables laid out that we know for sure, correct? And we are trying to find how long it takes, the seconds, or yeah, let's put t instead. Sorry, not that. But let's do t equals question mark, correct? And so then we can just see the difference or the change from the final and the initial is 12 meters per second, right? Because we're trying to find how long it takes for this to speed up from 8 to 20, correct? So basically, and if it's accelerating at 2 meters per second squared, and you're trying to cover the velocity of 12 meters per second, we know that what? We know that the final velocity is equal to the initial velocity plus a t, correct? This was an equation we derived last time, and this is one of the more logical ones. Yeah. Okay. This is the one of the more logical ones. If we remember, we have our three variables, correct? We can just input it now. 20 equals 8 plus um 2t. So when you get that, we found the difference, which is 12, equals 2t, and then t equals 6 seconds. Currently, I did not put the units. I should have the units up, but for time's sake, I did not have the units for this section. It's always a good habit to put it. But again, we got this equation from last class. I'll just go like it's pretty obvious, right? I'll just do like a quick 30-second review of what how we found this out last time. If Bob starts from rest and wants to go 20 meters per second, right? We need to find out like um how long he's accelerating for and for how much time, correct? So let's say he needs to accelerate from 0 to 20 in 10 seconds. That means he has to constantly accelerate at 2 meters per second squared in order to reach that, right? So when you multiply these two numbers, you get the final velocity. And when you can rearrange it and kind of get whatever you want, correct? I hope this makes sense. If it doesn't, please go to last class's recording, and I go in depth with this a lot more. Um, let's move on to the next question. You guys got that, right? Just put a yes or a no if you guys got it. If you guys have a question about something, I'm more than happy to answer. Yes, yes, yes. Okay, let's move on to the next one. Clear all drawings. I can go ahead and clear, right? No one's. Oh, sorry, it's not letting me clear for some reason. Ethan, is it letting you clear? Oh, there we go. Now it's clear. Okay. This I'll give you guys another 2 minutes. I think I gave, yeah, I'll give you guys until 24 to do this one. This is almost like, yeah, I'm not gonna say anything actually. I think you guys got it. Oh yeah, okay. I'm gonna give you guys one clarification. In this case, going to the going to the right is positive and going to the left is negative. I think you should probably assume. Yeah, it's sorry. This is to the right, and this is also to the right. Good, good, good. I have three answers so far. Ethan, how many do you have?
One.
Okay. Okay, a little more time. Okay, I'll give you guys a little more time. And then in the meantime, how do you guys feel about the homework? Because I know like some of you did do it, but a lot of you guys didn't do it. So do you guys like do you think the homework just you guys didn't have time to do it or you guys didn't feel like doing it? Like um yeah, just ponder on that while I do this question because I think you got if you guys still didn't um if you guys didn't finish the question, that's okay. I'll just be walking through it with you guys because um yeah, because if we have to get through this, we have a lot to cover. Okay, so again, this is pretty similar to the previous question we had. We're using almost the same, or we are using the same equation actually. We have we always want to start with our variables, correct? We have three variables that were given. The initial velocity, which is 30 meters per second, the final velocity, which is 18 meters per second, and the time, which is equal to 6 seconds, correct? And so from now, with this, we can start to kind of mold it, right? We actually technically also need the equation, but you guys can figure this out by deriving it as well. But I'll put it up for you guys. Correct? We have everything we need to solve, right? Now it becomes really simple. All we do is we just input, input, and input. Correct? Once you input everything, you get 18 equals 30 plus 6a, right? And when you solve this, you get minus 12 equals 6a. So you get negative 2. I didn't put my units here again because I should, but for time's sake, I won't. And I know that we're solving for the acceleration. So we're always going to have meters per second squared, correct? A equals negative 2 meters per second squared. And when you get an answer like this, it's always good to put it into like a visual, right? If you see a negative 2 meters per second squared, a lot of you guys did it in chat, and I'm very happy with it. And even if you guys didn't put in chat, I understand what you guys mean. I have full faith that you guys do know what this means, but um it's always great to put it in a visual. So when I see a negative 2 meters per second squared, I'm already thinking that this train is kind of decelerating from 30 meters per second to 18 because I see that negative, right? If I just saw a 2 meters per second squared, I would assume it's accelerating until I was given otherwise, correct? Does that make sense to you guys? Can I move on? Do you guys have any questions? Didn't have time. Makes sense. Makes sense. Good. And then I see a lot of you guys said you didn't have time for the homework. That's totally okay, right? This homework's for you guys to kind of just get more practice with it. So
And
yeah.
also, the homework is gonna remain open for submission. So if you have time to do it later, you can always just do that and then submit it. So yeah.
Hmm. And also, if you guys don't think you guys have problems for like or time for all the homework problems, just do one or two, just to get a feel for it. You don't have to do all of them. Just submit one or two. We'll be happy to see that we'll be happy to see that you guys like just did the homework, and you guys get it. Don't worry too much about the points that we're giving out. Um, if you see like if you tell us beforehand that you didn't have time to do the homework and you could only do the homework was given on the Google. Are you in the Google Classroom, Ria? Ethan, could you link the Google Classroom once more? But the so we linked the Google Docs with the homework, but like if you guys tell us beforehand, oh, I only had problem or time to do one or two of these problems, we'll give you the points you deserve. Like if you get we'll give you the 20 out of 20. We're just happy to see you guys doing the homework whenever you guys can. So this class is not going to be very rigorous in. Terms of homework. Next question. Okay. This one's a bit a ball at 15 meters per second slows uniformly at negative 3 meters per second squared. How far does it travel before coming to rest? Give me a second. I'm gonna change my location. This one's a bit harder, so I'll give you guys until 33. Um, uh, how much time do you guys need? Or do you guys think you guys are good? Okay, I'm going to go ahead and solve it now. We got a couple of different answers, and that's totally okay because this is a bit of a harder question. But let's start with identifying technically our three variables, correct? Okay, we have the initial velocity, which is 15 meters per second, our acceleration, which is -3 meters per second squared, and our final velocity, which is technically 0 meters per second, correct? Because coming to a rest just means when it has zero velocity, correct? So when we solve this, again, we're gonna use our four equation, or we're gonna pick and select our one of our four equations that we had from last class. And there's a few ways to solve this. You can use a few different equations because you're given um the variables, but I would go about using the VF squared equals VI squared plus 2AX equation, correct? Because this has all three of the variables, and then we can just sorry, I don't know what I did there. This has all three of our variables, and then we could just go ahead and solve for x, right? Um, so let's go ahead and input it and see what we get. 0 equals what? 225 minus 6x. 6x equals 225. X equals 37.5 meters. I think that's correct. Um, Another way to solve this is like figuring out that it takes what? It'll take 5 seconds for the velocity to be zero. So if we know that this is all of this is happening in 5 seconds, we can use x equals VIT plus 1/2 AT squared. We can also use this equation to solve for it. Either way, you get the same answer. But I think it's just easier to use this one because we're already given all three of our variables, and I think it just makes more sense. Does anyone have any questions on this? Because I know this one was a bit harder. So yeah, feel free to private message me if you guys have any questions, or just private message Ethan. You don't have to message to anyone if you guys think that you're not comfortable with that. But if not, I'm gonna delete what's on the board. So if you guys do have a question, go ahead. No? Okay. I'm gonna move on to the next one. E. Ethan, can you erase my board? Is my
You can't.
8? Sorry, let me reshare. I don't know why it did that. Is it because I was in? Sorry, guys. Yeah. Okay. There we go. There we go. I'm back to annotating. Okay, perfect. Sorry. Um, this is a hard question. Do you guys want to go through this now that you guys are a bit more practiced in kinematics? Yeah, yeah, yeah. Yeah. I'll give you guys 5 minutes for this one because I know this is a bit harder. So and if you guys don't get it at any step, you can just ask us a question and we'll be able to um answer the step that you guys are on with the problem so we can move on or you can go forward with it. I'll give you guys a few more minutes because I've only gotten two responses. Um, just a text if you guys needed more time, or else I'm gonna get started with the problem. Okay. I think I can get started. So I'm a bit curious on some of your guys' answers and how you got them, but I'll explain the answer first, and then if you guys are like, I want to know where you guys got the answer you guys got. But I'm gonna get started. So let's start off with what we do every single time. We're gonna label our variables. So we have t. Oh, sorry, okay. We have t equals 0 and x equals 0. I'm gonna say xi, right? I'm gonna say xi and t1, right? These are variables you guys will be like practice using because so you see how we see a reoccurring theme of uh like the sorry. Like you see how we see t twice and x twice, and so you'll be seeing quite a bit of that. So we're gonna get t sub 2 equals 6 seconds. I'll put my units in there. And we get x sub 2 equals 0 meters again, correct? So, and then the velocity we have is what? Initial velocity is 12 meters per second. Correct. We have all our variables. And now this will be using um a few equations combined. Okay. So what we will do is first we're gonna find out the acceleration because we have to find out the because we know that it's undergoing constant acceleration, right? And to find the maximum positive displacement, we have to know what this constant acceleration is. So we can do that using one of our equations, correct? We have x equals vt plus 1/2 at squared, correct? We have our x, or sorry, yeah, we have our x, which is what, 0? We have our v, which is 12. We have our time, which is 6. Oh yeah, for this, we're using this to find the velocity or the constant acceleration. So equals 12 times 6 plus 1/2 of a times 36, because 6 squared is just 36, correct? So then we get 18a equals 70. Sorry, I messed that up. 18a plus 72 equals 0. We get negative 72 equals 18a. We get a is equal to negative 4 meters per second squared, correct? Is everyone following up until this point? Yes. I saw one, yes. Everyone else? Okay, I'm seeing more yeses now. Okay. Okay. So now we know this acceleration, correct? So now we'll try to find the now we can try to find this maximum positive displacement because we know the acceleration undergoes, right? No one did everyone try to find the acceleration beforehand, or were you guys just straight trying to go into the maximum positive displacement? Okay, I'm gonna assume you guys try to solve for the other ones first. But um so we know that the maximum positive displacement will happen at 3 seconds, correct? 3 seconds. If you guys want to know how I got that the maximum positive displacement will happen at 3 seconds, that's because we know that it'll reach its maximum point once the velocity of the final equals 0, correct? So once v final equals 0, we can use this equation we have, right? Once this variable equals 0, we can just set 12 plus, sorry, 12 minus 4t, because we know that the acceleration is this. So we get that t equals 3 seconds, right? That makes sense to you guys, right? This is when the maximum positive displacement will happen. You can also just use like your intuition, right? It makes sense that it'll reach its maximum positive displacements once it's 3 seconds in because there's constant acceleration and it has to return back to 0 both ways. So I just this is a way to prove it. I don't think there's like this is necessary if you guys um know that, but so if we know that it's 3 seconds, right? We can just input that back into the equation. We get so now we're trying to find it at the 3 second mark, correct? So we found this new variable for t. Well, let's call this t sub 3 for some reason, because why not? We know the initial velocity is still going to be 12 meters. We have our acceleration of negative 4 meters per second. So now we can finally solve for this x, right? 12 times 3 minus, sorry, plus 1/2 of a negative 4 times 9, right? I did that right, correct? This is kind of what we get once we input it back. And once you solve this, I don't want to go through the hassle of solving that, but you get 18. Yeah. So you get 18 meters is the maximum positive displacement. Does that make sense to you guys? Is there any place you got? I know I breezed through this part, the last part pretty quickly, but does that make sense to you guys kind of how I got that? So I know some people said there was two people or three people that said 36 or 72. Do you guys get why it's not 36 or 72 and it's actually 18? Yes, yes. Okay. Um I'm gonna go quickly through these problem solving tips and then I'll give you guys a quick 3-minute break to go get whatever you need. But I'm pretty sure we did most of these. Um you saw me do it at least once in a problem, most of these. So I didn't drop dry diagram for any of them. I don't think we needed to. It was pretty, but for this one, I did talk about choosing a positive direction. I think this was also pretty self-explanatory in all these problems. Once you get a bit more confused, I think that's where like once you get bit more confused with your positive negatives, maybe that's where it gets a bit confusing. But you always want to define your what's positive and what's negative because in some cases, up could be negative, up could be positive, down could be negative. But if you have up negative, then you have to have your down positive, correct? So that depends. We always did this. We always did this. We always listed our values. We tried to identify the equation to use for our unknown values. We selected the appropriate equation. We solved algebraically before substituting the numbers. This is basically just substituting the numbers in for the correct thing that we're trying to solve. And then um, you guys did your units pretty well on one when you guys were giving your answers. So I'm happy with that. I don't think I'm gonna be too picky about I'm gonna be picky about the units, but you guys are doing a good job with it. Um, Great. Good, good, good. Let's see what's next on our agenda. Oh yeah. Sorry. One more thing before you guys get the break. Yeah, one more thing before you guys. This is just a quick um like I'm pretty sure these are the equations that we this makes it okay. I promise this looks more complicated than it actually should be. These two are just basically the things we were doing in class. This is just VF equals VI plus AT. And this is just x equals VI t plus 1/2 AT squared. But all of this is going to be horizontal, correct? This doesn't account for like any acceleration upwards or downwards. And if the acceleration is equal to 0, then this makes sense. This gets canceled out and this just gets canceled out, correct? If it's just 0. Um, vertical motion's a bit harder, but I think it's more fun. Um, so G, I think we'll be covering this in our next like in the next slides as well, but G is going to be the gravitational acceleration, correct? I'm not going to write it out, but G is equal to the gravitational acceleration. So it's just a defined type of acceleration. So what we did instead of taking this a sub x, we just substituted it with g. And since they're taking gravity downwards to be negative, so this is why it's minus g instead. And then again, it's minus here because it's negative. And then all of these, they're just substituting g for acceleration because this is again vertical. So g plays a vertical component. And yeah, you can read the rest of the slides, but I'll give you guys a break for 5 minutes before the next topic we start. You guys can check on the score, the FIFA score, or whatever you guys need. Oh yeah, make sure you guys do your attendance, by the way. Um, it would be great if you guys did that. Okay, are you guys good to go? I don't know if we'll get through all of these slides, but I definitely want to get through the beginning, and especially because there's eight or nine people here, so I think a good foundation would help, and then next time we can get more in depth when there's more kids, so they can just kind of tag along. But let's get started. Today, the main topic will be about energy. Just a quick, like it'll be a basic foundation of energy. And do you guys like can you do you guys know about kinetic and potential energy? Yes, have you heard those terms before? Put put some examples in chat of what kinetic energy or what potential energy is. And if you guys don't know, that's okay as well. That's what we're learning today. Can you guys think of examples or okay, kinetic energy is about motion. Okay, we're getting somewhere. Okay, let's start. Okay. Um, so what is energy? Okay, it comes in many forms, right? It comes in mechanical, thermal, nuclear, chemical. It comes in all types of forms, right? The two main types we'll be focusing on is kinetic energy and potential energy, right? This is under like the mechanical energy where like the energy is related to motion and position, correct? And when we talk about kinetic energy and potential energy, for right now, we like to say it's conserved, right? So like the energy is not like neither created or destroyed, right? So if you have a set amount of potential energy, let's say you have like a roller coaster, right? And it starts at the top. It has a lot of potential energy. And ideally, all of that potential energy will get transferred into kinetic energy at some point before it comes to a stop, right? You ideally it won't like lose any energy between then, but of course there's friction and air resistance and all that does get accounted for in reality. Right. So energy is just the ability to do work or cause change. That's the simple definition. And like we talked about earlier, there's two types, kinetic and potential energy. I think I saw someone say it in chat, but potential energy is the stored energy, right? So that's the one that, like, if you look at this roller coaster here, the potential energy would be up here, right? It would be stored up here and then it goes down, correct? And it might still have kinetic energy from beforehand. This is not too great of a picture because I can't see the top, but that's where it gets stored, and then it depends on height, mass, and gravity, correct? You need to remember that for the next few slides because there's an equation that we can use from that, right? And for kinetic energy, that's the energy of motion. That's when it depends on the mass and speed, right? So as the kinetic energy increases, the speed also increases because it depends on speed, right? And when you're looking at this, you notice that the only two things related with potential and kinetic energy are mass, correct? The other two, like height and gravity and speed, are not related. Because when you're talking about speed, we're talking about velocity. And when we're talking about gravity, that's acceleration. And then there's also height, right? So if we know the speed of an object, we can also figure out the potential energy. But if we know the height height of an object, we can figure out the kinetic energy. And we're assuming that gravity, for right now, we'll just make gravity equal 10 meters per second squared. Technically, it's 9.81 meters per second squared, but to make it easier for you guys, we'll just say 10. Um, so again, kinetic energy is the energy an object has because it is moving. It depends on mass and velocity. If an object is going at the same velocity, but its mass is increasing, then that has more kinetic energy. If it has the same mass and velocity is increasing, then it has more kinetic energy again, correct? And this is the formula, 1/2 mv squared. Um, we will derive this next class because it takes a few other equations to figure out um why this is. But for right now, we can just use, yeah, actually no, I won't cover it too much. But just remember, you might want to write this down. But the equation is 1/2 mv squared. That's the write it down in the notebook and then make sure you also have the units, which is joules. Joules is just equal to what? Kilogram meters squared per second squared, right? Because velocity is equal to meters per second. And then if you square that, you get meters squared per second squared and then times kilograms. So that's what joules is equal. That's the term for energy. You'll be seeing joules a lot when you're working with um energy. And all of these are examples of kinetic energy. Like if you're moving in a car, that's kinetic energy, throwing a baseball, anything like that, correct? Um, yeah. In this case, direction doesn't matter and it cannot be, yeah, that's actually a good point. Um, when you're working with energy, the direction does not matter, right? If you think about it, there's no certain direction you can put energy in, right? So when you square a negative number, it just becomes positive. So um, it'll always be positive because mass won't be negative either, correct? So, some cool things to know is that if you double the speed, then the kinetic energy will quadruple because it's squared. But if you double the mass, then the kinetic energy will double. Like these are just cool patterns you can notice. And yeah, potential energy is like again the stored energy. This is a better picture actually. If you look right here, yeah, if you look right here, this is probably where the most potential energy for the ride is, correct? Because let's say this is the height and it's facing a g, it's facing a gravitational acceleration of 10 meters per second squared, correct? So we can say that more participants on this ride would ideally correlate to more potential energy, right? But again, there's things like friction that play a role and stuff like that. So maybe all that energy doesn't get converted. But yeah. So I think we get into this. Yeah, so the height itself doesn't matter. That's also a great point, right? So if you're taking the height from here, when I was saying this, right? When I was saying this is the height, I was taking it relative to this point, correct? I was saying that this is the change in height. So that's what that previous slide was saying, or the next slide was saying. It depends on the change in the height. A lot of this is just like repetition. It's just different ways to explain it. So if you get it one way but not another, that's fine. I don't want to confuse you guys too much. But yeah. You can use it, you can set potential energy to zero. We'll be working with that probably later. I don't see where we would use that right now, but yeah, this is the equation. This is the thing I want to point out. This is the equation, right? You saw mass times gravity times height. Or you saw that it depends on all three of those things. You just multiply them together, right? It makes the most sense. So, um, yeah, when you have, and the units also matter here. So be careful of the units. Again, if you notice, it still uses joules because this is also kilogram meters squared per second squared, correct? That's something cool you guys can notice. Yeah, but so if you look at this apple, if you look at this apple, let's say this has some certain mass m, and it's dropping a height in change of height h, correct? So then the apple would have potential energy of mgh. We go, yeah. Um, so it's like I said earlier, I don't know if you guys remember, but we conserve the mechanical energy, so we ignore friction and air resistance usually, right? Like if we ignore the friction and air resistance that goes along with the roller coaster, the max. So if we draw an image here like this, right, with the height h, the maximum potential energy would be up here, which means that there is very low kinetic energy, right? Because kinetic energy is the energy of motion, but it's not moving way too much up there. It's just sitting, which has a lot of potential energy. As soon as it turns that corner, then it's kind of like a inverse graph, correct? Then the kinetic energy starts to increase and the potential energy starts to decrease. And then near the bottom is where the kinetic energy is the max, and there's the lowest potential energy. So I just wanted to get the point that with mechanical energy, it's usually conserved and it doesn't just disappear. It just changes the form, right? Um, what is? I think you can just do question two. I think question two is the most interesting. So if you want to do all three questions, go ahead. But um, focus on question two. And then get to question three if you can. Question three is also whatever. I'll give you guys 2 minutes to do question two real quick. 321. Oh, that's great. You guys are doing all of them. That's good. Are we good to move on? Or So if you guys, yeah, I'll just go on. So for question two, question one, it's just it gets converted into kinetic energy as it falls. Question two, if we look at the equation we used earlier, right? 1/2 mv squared. Again, we know that we can input this and this, so you get 8 joules. Oh yeah, this is where I would like the joules. I know you guys just said first option, which is totally fine as well, but if you did sulfur, you would put 8 joules, and then for the second one, you just get 4 joules if you inputted it. And clearly 8 is bigger than 4, so it has more kinetic energy. And then the third question is just um it increases its potential energy because as you increase height, um the the potential energy will increase because mgh, if you multiply by a higher number, you get a higher thing. And if you look at the equation as well for potential energy, you'll notice that it can't be negative either. Um, are we good? Let's let's quickly go through work energy theorem. This is very important to go through. But so the work energy theorem is basically relating what we just talked about to work, which is um like talking, so work equals force times distance. But basically it states that the net work done on an object is equal to the change in its kinetic energy, which makes sense, right? In some sort of case, correct? Because if a ball moves, or if a ball has a final kinetic energy of 8 joules, and its initial kinetic energy was, let's say, 2 joules, right? The work done on that ball is 6 joules, correct? So if you think about it logically like that, I think for me at least it makes pretty good sense. But like if you look at this guy, the guy moving the boxes, you can just use his like previous velocity and his final velocity and subtract it with his previous velocity, because a lot of the times this component will stay the same and their velocity is the only thing changing, right? Let's say a ball is moving at 8 meters per second, right? And then over here at distance, what? Let's say at distance 0 meters, it's moving at 8 meters per second, and at distance 10 meters, it's moving 8 meters per second. Can you tell me the total work it's done over that period? And this is sort of a quick trick question, but we're assuming that it has the same mass. And it's just type in chat what you guys think. And you could probably figure out the answer by looking at some of the things over here. But if you don't, that's also fine because it's a tricky question concept to understand. I'll give you guys a minute before I answer it. How much work has it done? Okay, so I didn't get any answers, but I'm just gonna go over it pretty briefly. Um, so technically it's done zero work, correct? Because this has a total of zero work done. Because if you look, the velocities stay the same and the masses are the same. So if everything's constant, it's just moved a distance, correct? It hasn't actually there hasn't been any work done to that ball to change that velocity. So technically there's no work that has been done on that ball. You can even see like if work is done by an object, its speed would increase, or if the work was done by an object, its speed would decrease, correct? It's just looking at the final velocities of the initial and the sorry, it's looking at the velocities of the final kinetic energy and the initial kinetic energy. Okay, this is what I talked about earlier. Work also equals the force done by an object times its distance, right? So I think this is also pretty you can visually just explain this self to you. But if someone's applying 5 newtons of force over 10 meters, then it's just gonna be 50 joules of force, right? It's gonna be using the same exact component that we were using with the previous slide because it is still technically um, a form of energy. So if you're applying, if someone's lifting, if someone's applying 10 newtons of force to lift a box, this is messy. If someone's applying 10 newtons of force to lift a box, what, let's say 3 meters up, then the total work, let's say John has done is 30 joules of work, correct? Does that make sense to you guys? That's basically just both of these in that example. Yeah. And to be clear, you can do negative or positive work, correct? You can technically, in this case, like this is where um you translate that kinetic energies. Like that's where you use like delta or the change in of the kinet of the change in the energies to find out where the work has been done. I think that is it. We'll go over the check-in next class because we can go over with more people who join to review as well. But we'll be giving out homework as well this week. We hope you guys do it, but if you guys don't have time, that's okay. Get through as much as you can. But if you guys have any questions, feel free to stay and ask. But as if, oh yeah, make sure you guys also fill in the attendance, the Google Classroom thing. Please do that so we know who attended this session. Is it hard? The homework? Um, no, it's not going to be too hard. I'll make sure it's like because we didn't cover too much in depth for kinetic energy and potential energy today. So it won't be too hard. It'll just be figuring out the energies of certain objects. But yeah, maybe I'll put a work question in there just to give you guys a review. But other than that, I think it shouldn't be too bad. Good. You guys are free, feel free to leave now.